By the end of this video, you're going to be feeling much better with implicit differentiation. We're going to be going through 4 problems in this video, and these problems will be getting harder as we go. And of course, if you're looking for the notes for this video, as always, I have the printable notes linked right in the description. Now, our first problem says, given that x squared plus y squared equals 25, find y prime. Now, for our regular derivative problems, like let's say find the derivative of y equals 2x plus 5. We're used to seeing that y being solved for, just taking the derivative on both sides from there, and that's how we get our derivative. But now we have the y in the equation, right? It's not solved for on one side. And so when we have a function where y isn't solved for, or it can't easily be solved for, that's called an implicit function. And when we try to take a derivative of an implicit function, that is called implicit differentiation. That's what we're going to do here. Now, implicit differentiation is very similar to the differentiation that you already know. We still start off the problem in the exact same way by taking the derivative on both sides. So we're going to take the derivative of the left-hand side, the derivative of x squared plus y squared. And that's going to equal the derivative of the other side, the derivative of 25. So now let's just go through and take our derivatives. First, we have the derivative of x squared, and that's 2x. That's just power rule. And then we have the derivative of y squared. And this is where everything starts to get a little bit tricky. Now, the derivative of y squared is going to be 2y, but you're going to have to tack on a y prime. But why? Why do we have to tack on that y prime? Let's talk about that. Now, we just did the derivative of x squared. We know that's 2x, we know that's power rule. But we could also take this derivative with chain rule. You can take any derivative with chain rule. It just really doesn't make sense in a lot of cases like this one. We know the derivative is 2x. Now, if we think about this with chain rule, the 2x, that's the derivative of the outside leaving the inside alone. And then with chain rule, we have to take the derivative of the inside. Now, the inside function, we can think of this x as being trapped under that square. And so the inside function is x. The derivative of x is just 1. So if we did this with chain rule, we still get 2x. We just have this times 1 on here that really doesn't matter much. That all changes when you start talking about the derivative of y squared. Now, if we do the derivative with respect to x of y squared, things start to change because, well, we still get that 2y. But now the derivative of the inside, the derivative of y, that's not 1. We have the derivative with respect to x of y, right? That's the just notation for derivative of the inside, derivative of y. We know that d dx of y, that's dy over dx, right? So this is 2y times dy over dx. And writing that in a slightly different way, we can write that this is 2y times another way of writing dy over dx is we can just write a y prime. That also means the derivative of y. And so what effectively ends up happening here when you take derivatives of y is you take the derivative as if it was just a derivative of x's, but then you tack on a y prime at the end. So the derivative of y squared, if we just think about power rule, right, that would give us a 2y. But because you really have to think about this with chain rule, the chain rule will actually give you that extra y prime, because the derivative of the inside isn't just 1 like it is with x's. So that's why the derivative of y squared is 2y y prime. So that's the derivative of the left-hand side. But the derivative of the right-hand side, that's just the derivative of a constant, and that's 0. So now that we've taken that derivative on both sides, really all we have to do from here is solve for y prime. So let's do that. This will be quick. We'll start off solving for y prime by subtracting 2x on both sides. And doing that, we'll get 2y y prime is equal to a negative 2x. And then, really, the only other thing we have to do to solve for y prime is divide by 2y on both sides. And if we go and do that, what we end up getting is that y prime is equal to, well, you can see that the 2's cancel off here, so we can actually just write this as negative x over y. And that is our derivative of y. Now, there's one little note that I want to make here. You can see that our derivative has a y in it. And, usually with our derivative problems, we never get a y in our derivative. So why do we have a y here? Well, actually, it's for good reason. If you think about the graph of what equation we're dealing with, what function we're graphing, right? X squared plus y squared equals 25, that's a circle. And so let me just graph a circle here. Now remember, the derivative means the slope, right? So this function right here, this negative x over y, that's going to give you the slope at any point on this circle. And let's say that you wanted to find the slope at, let's say, x equals 2. Well, would that mean that you're talking about this point or this point? You have to specify a y-coordinate so we know which point you're talking about. They have very different slopes. The slope here is completely different from the slope here. So that's the need for the y-coordinate right there. And yeah, that's problem 1. So let's move on to a little bit of a harder problem. Given that x to the 4th plus x squared plus y cubed is equal to 5, find y prime. Again, we start off this problem in the exact same way. We take a derivative on both sides. So we do the derivative of x to the 4th plus x squared plus y cubed. And we do the derivative of the other side, so the derivative of 5. Now, taking these derivatives, we have the derivative of x to the 4th. We know that's 4x cubed. Just a little bit of power rule there. Then we have to add the derivative of x squared, y squared. And that is actually a product rule. That is two functions that are being multiplied together. And remember, the product rule is that the derivative of u times v is u prime v plus v prime u. So what we're going to have to do from here is take the derivative of x squared and y squared separately. And those are actually derivatives that we've already talked about. So that should be pretty quick. We can take the derivative of x squared first. So that's 2x. So we write that, and then we tack on that y squared. So that's great, but we also have to take the derivative of the other piece now. We have to take the derivative of the y squared. And we know that is 2y prime. So we have that part, and then we just need the x squared tacked on. Right? And we don't take a derivative of it. We've already done that in the other term. Now, you could rearrange this a little bit, make this look a little bit nicer. What I would personally do is just write the x's first. So I would write it like this, but that's completely up to you. So that is the derivative of x squared, y squared. Now, lastly, we need the derivative of y cubed. And again, we're taking derivatives of y's here. We take the derivative just like if it was an x cubed. If it was an x cubed, it'd be 3x squared. So this time it's 3y squared. And then all we have to do is tack a y prime on the end. And then that's going to be equal to the derivative of the other side. The derivative of 5 is just equal to 0. So that's perfect. Now that we've taken the derivative on both sides, let's go and solve for y prime. This time it'll be a little more gross, but we'll be able to figure it out just the same. So let's take every term that doesn't have a y prime on it. That's those two terms right here. And we're going to move that to the other side. We just want terms that have a y prime to stay on the left-hand side. So that's going to require us to subtract a 4x cubed and subtract a 2xy squared on both sides. Now, you might not have to write all of this out and show all your steps. I figured I would, in case it's helpful to at least one of you. And when we subtract those two terms on both sides, what we end up getting is 2x squared y prime plus a 3y squared y prime is equal to a negative 4x cubed minus a 2x y squared. Now from here, what we can do is we can see that since both of these terms on the left-hand side have a y prime, we can factor a y prime out, and that's how we can get y prime by itself. And if we factor a y prime out, then what we're left with in the first term is a 2x squared y, and in the second term, we're left with a 3y squared. And that's equal to the exact same right-hand side. So, great, we get that piece. And now, factoring that y prime out really helped us because all we have to do now is just divide off everything that was left over from that factoring. We just divide that on both sides. So we divide off a 2x squared y plus 3y squared on both sides. So this piece goes away, and we end up getting that y prime is negative 4x cubed minus 2xy squared all over a 2x squared y plus 3y squared. And yeah, that's going to do it for problem 2. So this was a little bit harder than problem 1. We had some more derivatives to take. We saw a product rule, but what we haven't seen yet is trig functions. We haven't seen a sine or a cosine yet. So maybe let's do a problem next where we're dealing with those. That's problem 3. So problem 3 says, given that sine of x plus y equals y squared cosine x, find y prime. And okay, again, take a derivative on both sides. Start off the exact same way. We have the derivative of sine of x plus y is equal to the derivative of y squared cosine x. Now, you don't have to write out this step, but if it helps you really see what's going on here, then I definitely recommend it. Now, let's take the derivative of the left-hand side first. Now, we can see that sine, it has an x plus y on the inside, not just an x, and so we're going to have to use some chain rule here. First, we know that the derivative of sine is cosine, so that's going to be the derivative of the outside, and we leave the inside alone, the inside being x plus y. And then what we're going to do with chain rule, we have to multiply by the derivative of the inside. And the derivative of x plus y, well, that's going to be the derivative of x, which is 1, plus the derivative of y. And the derivative of y is y prime. Right, remember that the derivative of y, that is what we call dy over dx. That's what we call y prime. So that's where I get that piece from. Now, I don't really need this extra multiplication symbol here, so actually I'll just slide these together, and you'll know it's multiplication. And then we can move on to the derivative of the right-hand side. And the right-hand side has two functions being multiplied together. So what rule are we going to use to take this derivative? We use the product rule. What I'm going to do is take the derivative of the first piece, the derivative of that y squared. And we know that the derivative of y squared, we've talked about this a bunch in this video, it's going to be 2y with that y prime tacked on. And then we multiply by the second function. We multiply by cosine of x. And then we're going to add on, here's our second term, we're going to take the derivative of the second function now. And the derivative of cosine of x is negative sine of x. And since that's negative, what I'm actually going to do here is I'm going to make this sign a negative. And I'll put my sine of x in. And then we multiply by y squared. We don't take the derivative this time because we already did that in the first term. So you can write that as sine of x y squared. Personally, I'd rather see it as y squared sine of x. I like to have my trig functions come after. And yeah, so that's how I'd clean this up a little bit. But from here, we're good to go and solve for y prime. And to do that, we would be able to get all of our y primes over to one side, just like we did in problem 2. Like in problem 2, when we finished taking derivatives, this thing is what we had. And we were able to get our y prime terms to one side like this. But there's a little bit of a difference here with problem 3. With problem 3, you can see that we have this 1 plus y prime being multiplied by the cosine of x plus y. That's not a clean term. There's some distributing that needs to be done. First, the cosine of x plus y multiplies to the 1, and that's just cosine of x plus y. And then the cosine of x plus y multiplies through to the y prime. And that gives us plus y prime cosine of x plus y. And that's going to equal, well, our right-hand side is going to stay the same. 2y prime cosine of x minus y squared sine of x. So now that everything's distributed out and we have our clean terms on the left-hand side and the right-hand side, we can go through and get all our y prime terms to the same side. So what I'm going to do is I'm going to subtract 2y prime cosine of x on both sides, because then I get all my y primes to the left-hand side. So subtracting 2y prime cosine of x on the left-hand side, there we go. And then, well, I'll have my 2y prime terms on the same side, but I have this extra term here, this cosine of x plus y, that doesn't have a y prime in it. And so I want to get that over to the right-hand side, and so I subtract it on both sides. So subtracting cosine of x plus y. All right. So doing that, what we're left with is y prime cosine of x plus y minus a 2yy prime cosine of x is equal to a negative y squared sine of x minus a cosine of x plus y. And now that we have all our y primes on the same side, we can just factor that y prime out. So, factoring the y prime out, we're left with a cosine of x plus y minus a, in the second piece, we're going to be left with a 2y and a cosine of x. Right, just take out that y prime piece. That's the only thing that changes. And that's going to, again, equal the same exact thing that we had on the right-hand side. That's the negative y squared sine of x minus cosine of x plus y. Okay? So the last step in solving for our y prime here, we just take everything that's multiplying y prime right now, and we divide it on both sides. So we divide cosine of x plus y minus 2y cosine of x. And I'll just cheat a little bit here because I don't want to write that all out again. Getting lazy here. There we go, copy paste. So now what we end up with as our answer is that y prime is equal to a negative y squared sine of x minus cosine of x plus y all over a cosine of x plus y minus 2y cosine of x. And yeah, that right there is the answer for problem 3. So now we've done some work finding y prime, but what if you were asked to find y double prime? What would you do then? Well, that's problem 4. So, problem 4 says given that x to the fourth plus y to the fourth equals 16, find y double prime. Now, we're going to start off by doing the exact same thing that we've been doing for all 3 problems. We're going to take a derivative on both sides. The first step is just to really get y prime. So, we're going to take a derivative on the left. That'll be the derivative of x to the fourth plus y to the fourth, and that's going to equal the derivative of the other side, the derivative of 16. Now let's see if you can speed through these derivatives here. First we have the derivative of x to the fourth, and we know that's 4x cubed. And then we have the derivative of y to the fourth. And again, you take that derivative in the exact same way that you would take it if it was x to the fourth, right? So we're going to get a 4y cubed. But since we're taking derivatives of y, we tack on a y prime. And that is going to equal the derivative of the other side. And the derivative of 16, the derivative of a constant, that is just 0. So now let's quickly go through and solve for y prime. We'll first start off by subtracting 4x cubed on both sides. And doing that, we're going to end up getting 4y cubed y prime is equal to negative 4x cubed. Now the last step for solving for y prime is just going to be dividing by 4y cubed on both sides. And doing that, well, we can see that the 4's cancel off, and we get that y prime is equal to negative x cubed over y cubed. That's y prime. But remember, we're asked for y double prime here. So what we need to do is take another derivative on both sides. So what I'll just do is I'll write it like this. Take a derivative on this side, and we need to take a derivative on the right-hand side. Now, the derivative of y prime is y double prime. So that already gives us what we want. But now we have to take the derivative on the right-hand side. That's where all the work comes in. That's actually going to be a quotient rule. If we want to do this out with quotient rule, remember that the quotient rule is the derivative of u over v, which is u prime v minus v prime u all over v squared. You might have a different way that you like remembering it, but personally, this is the one that I like best. So, in any case, u here, that's the top function, that's negative x cubed. And v, the bottom function, is y cubed. So from those, we can find our u prime, the derivative of the top, and v prime, the derivative of the bottom. Now the derivative of the top, the derivative of negative x cubed, that's going to be a negative 3x squared. And then the derivative of the bottom, the derivative of y cubed, that's going to be a 3y squared. Just take that derivative with power rule, but then you also have to tack on that y prime. So that gives us everything that we need to plug into the quotient rule. So remember, we get u prime v, that is negative 3x squared, times v, which is y cubed, and then this is going to be minus v prime u. So it's going to be a 3y squared y prime, and multiplied by u, which is negative x cubed. And remember, that's all over v squared, which is a y cubed squared. So that's our derivative done out with the quotient rule. So we got to do a little bit of simplifying here. And first off, I can see that I can just combine this. This is negative 3x squared y cubed. And then I have two negatives here, so I'm going to make this second piece a positive. And then I'll put the x cubed before the y squared and y prime. I'll write this as 3x cubed y squared y prime. And then in the denominator, I have that y cubed all squared. Remember, when we have something to a power being taken to another power, we multiply the powers. So the denominator is going to be a y to the 3 times 2, and that's 6. Okay? So that should be our answer here, right? And we should be done with the problem. Well, not quite. We're almost there. There's one more thing that we need to do. This y prime here. We already know what y prime is. We found it earlier in the problem, right? Before I made it kind of gross by taking the derivative on both sides, we had that y prime was equal to negative x cubed over y cubed. And what we should do is plug in that y prime is that, because then we'll get our y double prime completely in terms of x and y. So we'll be able to pick a point, an xy pair, and you'll immediately be able to tell me what y double prime is. You won't need to know what y prime is first. So let's plug in for y prime. We get that y double prime is equal to negative 3x squared y cubed plus 3x cubed y squared, and then y prime is negative x cubed over y cubed. That's all over y to the 6th. Okay, so what you end up having here, the y squared will cancel off with 2 of the y's down here, so this will end up becoming a y to the 1st power. But how do we get rid of that y to the 1st power here? Because we really don't want a fraction sitting up here. It'd be nice to get rid of it. Well, all we have to do is just quickly multiply by y on top and bottom. Or we'll multiply by y on top and bottom, and what that'll do is that'll cancel off the last y. So now we'll have the y's cancel off. And so what we'll end up getting is that y double prime is equal to a negative 3x squared times y to the, remember we're multiplying by that y on the outside, so this is going to be a y to the 4th. And that's going to be a, well, we have a negative up here, so this will be a negative, and then we have a 3. We have 2x cubed, so that'll make x to the 6th. And then the y's cancel off, so this y cancels off with the last y, so we're all set there. And then in our denominator, we have y to the 6th times y, which is y to the 7th. And yeah, Finally, we found y double prime, and that is going to be the answer for this problem. So yeah, that is implicit differentiation. Now, I know that stuff is a lot, right? You're going to want to do some practice problems to really get the hang of this, and that's why in the description, I made a worksheet for you guys with 12 more implicit differentiation problems on it. And if you want to work through those problems with me, I have an extra video in the description where I do exactly that. And I'll also include a link in the description to all of my extra videos on all the topics that I cover in calculus. So yeah, that's going to do it for this video. Of course, make sure you're subscribed to the channel. We're getting closer and closer to 100K by the day. And yeah, I'll see you soon.